Okay, then I guess I just continue. So perhaps let me remind you of what I talked about last time. So let K be a knot. And we were saying, okay, it's a good idea to look at the fundamental groups of the complement. And we also saw, like, you always have a working presentation. So you can always fairly easily find a presentation with, say, K generators and K minus 1 relations. And now we know that the abelianization of the fundamental group is isomorphic to Z. And if you're not as oriented, then actually you have preferred isomorphism of the abelianization to Z, namely which sends the oriented meridian to your generator of Z. And at least for my purpose, it's more convenient to think of Z as the infinite cyclic group generated by T, so like I write it multiplicatively instead of additively. So I call this map phi, which sends the meridian to T. And okay, now gets the slightly messy part. So the definition of the invariant. So let's just sort of work our way outwards. So I introduced Fox calculus, which is sort of like taking derivatives. And what you do is you take you differentiate every relation with respect to every generator. And what you get is you get a K by K minus 1 matrix, because K by K minus 1 possibilities of doing derivatives. And the derivatives lie in the group ring generated by the x1 to xk. But now you just apply your phi, so that instead of having an element in the group ring, you get an element in the group ring of T, but the group ring of the infinite cyclic group generated by T is just nothing but Laurent polynomials. So perhaps let me just stress this here. So in here, at that stage, we just have a Laurent polynomial in T. So right now, we have a K by K minus 1 matrix with entries whose entries are polynomials. And now ideally we would like to take a determinant, but we cannot do so because it's not a square matrix. And we play a stupid trick, which surprisingly enough works. Namely, so we have this matrix which is slightly elongated, so it has one row extra. And what we do is we delete one of the rows, take the determinant, and we compensate to remove ith. So we remove one of the rows and take determinant, and then we divide by the corresponding generator, xi minus 1. And for that formula to make any sense, we should not divide by 0. So the only condition we need is that we pick an xi such that the phi of xi is non-trivial. Okay, and somewhat miraculously, that the formula works. So it's like defines you an invariant of knots. Okay, and I mentioned some of the key properties. So number one is it's well defined up to multiplication by a power of t and a sign. Okay, so it's not totally well defined. You have a slight indeterminacy. Perhaps I also remind you the name. So it's called the Reidemeister torsion. Well, let me also say / Alexander polynomial. It's not quite the Alexander polynomial. It differs from the usual Alexander polynomial by a factor of t minus 1 in the denominator, but otherwise it is just the Alexander polynomial. Okay, and what properties does it have? So it's basically symmetric in T. So if you plug in T inverse, you get basically the same as just the original polynomial. So here the equals dot just means the equality holds up to my indeterminacy. Okay, and perhaps let me perhaps just write down here 2 examples. So here, if you have the unknot, then you get 1 over 1 minus t, or t minus 1, doesn't matter. And the other one is if you take the trefoil well, as I was saying, you get the same as the Alexander polynomial divided by t minus 1. So I can just here write t minus 1, and I guess most of us know. Oops, I'm going to screw up. The Alexander polynomial of the trefoil. So also, like if you had done my calculation with them, we wrote down the vertical representation for the trefoil. If you had done this calculation, you would end up with that result here. Okay, so here you see it's perhaps a little bit confusing the symmetry. So here, like if you take 1 over 1 minus t, so if you replace t by t inverse, it looks a little bit different. But then if you think about it for a second, you realize it's the same as 1 over 1 minus t times God knows what, minus t inverse or whatever. So it's not symmetric on the nose, but you will see it just differs from the original guy by a term of minus t inverse. Okay, and so the denominator here is always a slight nuisance, but okay, that's life. Okay, and what else? Then the next statement was that the degree gives you a lower bound on the genus. And now I rewrote it slightly differently from the last time. So now I write degree of tau. Now what does that mean? So first of all, if you have a polynomial, like a Laurent polynomial in T, by degree I just mean highest degree minus lowest degree. So basically, because I have this indeterminacy with the multiplication by t to the k, so I want a notion of degree, which is invariant if I multiply my polynomial by a power of t. So it doesn't make sense to define the degree as the highest coefficient, because you can make it arbitrarily larger. But if you look at difference and degrees which appear, then it makes sense again.
So in this case, it's really degree of the Alexander
polynomial. Minus 1, yes. So, for example, like, and now if you have a rational function, then by degree, I mean the degree of a numerator minus the degree of the denominator. So, for example, like here, the degree would be like on top, it's 2, like top coefficient is 1, minus 1, so you get 2, and then degree at the bottom is 1, so you get the degree equals 2 minus 1. Okay, and so the statement that it gives you a lower bound of the genus. So what's more, what you're more familiar with is perhaps that the degree of the Alexander polynomial gives you a lower bound of twice the genus. And now I divide it by t minus 1, so I have to compensate here by minus 1 here. In some sense, it's not as absurd as it sounds, because what you see here is minus the Euler characteristic of the Seifert surface. Because in some sense, if you think about it, if you work with a surface system, genus is in some sense not the right object. It's actually better to work with Euler characteristic. So in that sense, it's actually not such a bad formula. Okay, and the last statement was if k is fibered, so if the complement is surface bundle over S1, then you get equality. So and you get that tau is monic. So what do I mean by that? So that so polynomial is monic if top and bottom coefficient are both equal to 1. And now here, if a rational function, I mean it's called monic if it's a quotient of two monic polynomials. So for example, like here, the numerator, denominator both are monic, and so that's I call that a monic rational function. And for example, like the trefoil is fibered, and then it gets reflected in the polynomial here. I also want minus 1 here, yes. Thank you. Okay, yeah. Okay. And as I was saying last time, it's okay, it's a nice invariant, but it's no way a complete invariant. So let me have to do one more example. So if you take the white hat double of a knot k, so what is that? So let me just do it by example, e.g. So you take the figure 8 knot. So that's a figure 8 knot. And the weighted double is you basically double everything. Let's see, I'm going to screw it up. Okay, so if we now just connect, if we did just connect them in the obvious way, then there actually would be a link on two components. I prefer knots. So weighted double means you put in this clasp here. Okay, so now it's actually a knot, and that's called the weighted double of the figure 8 knot. And I know people who have taught knot theory and the weighted doubles know it's much safer to do it in an example with a figure 8 knot and never do it with a trefoil knot, because you have to be a little bit careful about your framing. But it's easier with a figure 8 knot. Anyway, so yeah, for any knot, you have a so-called weighted double. And it turns out that for weighted double, it looks the same as the unknot when it comes to that invariant. So here, tau weighted double of a knot k is just the same as over there, 1 over 1 minus c. Okay, so what it means is that that invariant, the Alexander polynomial randomized torsion, at that level doesn't see a difference between the unknot and the weighted double. Of any knot, yeah.
Weighted double is done with the 2 cabling only.
Yeah, so weighted doubling is
Zero frame weighted.
yes, exactly. That's why I picked the figure 8 knot. Anyway, in some sense, it's not so important the specifics. It's all what does count is it's fairly easy to come up with lots of examples of knots which are invisible, or which are invisible for my invariant. And sometimes it's not so important as a specific construction. Also, perhaps a proof of that statement with my definition might be a mess. Might be a mess. So the important thing is lots of examples which that invariant cannot distinguish from the unknot. It's the only thing which matters. Okay. Or perhaps let me just mention, in case you know the examples. So there are two famous mutants. There's a Conway knot, which I'm not going to embarrass myself by trying to draw. And it turns out. Oh, excellent. Okay. You just exposed the fact that I skipped Monday. Very naughty. Okay. So that's equal to 1. And I also like the Kinoshita Terasaka knot. Kinoshita Terasaka knot. You always get the slightly annoying 1 minus t at the bottom. Okay, so these are two famous knots which you saw on Monday, seemingly, and they are like 11 crossing knots and fairly complicated, but they have trivial invariant. And also, famously, they're also mutants of one another. And one of the properties of this invariant here is it doesn't see a mutation. Like many other invariants of knots, it just doesn't see a mutation. Okay. Okay, so that's life. And now the idea is to perhaps come up with something more powerful invariant. And yeah, so that's true for any knot k. Yeah. The only thing is you have to be a little bit careful what you mean by weighted double. This is a framing issue. Okay. So what's the idea? Okay, so now suppose we are given a representation of pi 1 of S3 minus k to, let's say, S ln C. Okay, so let's just say you're lucky, and somewhere in the streets you found a representation into S, L, and C of your knot group, and then we can see what we can do with it. And afterwards, we'll discuss some examples of which where such representations arise naturally. But right now, just assume we have such a representation. Okay, so what can we do with it? Define the following. So I've defined what I call a phi tensor alpha, which is actually a surprisingly simple object. So I now go to SLNC. So here now Laurent polynomials, and it's very simple. All you do is so you take your G and you send it to alpha G, which is just a matrix here. And now here I also have my phi, and remember the phi is well, basically my abilization. So what we do is we write here phi of G. So remember, so that is just power of T. Okay, so super harmless. You just take your representation, take your alpha, put it into one matrix, and one simple observation is that is actually still a representation, because the T, well, if you multiply a matrix with the T, multiplication with T commutes with the matrix.
Phi is just a Laurent polynomial, right? Phi G.
No, phi G is actually, it is a power of T.
So you multiply every entry of alpha G by 1.
Yeah, you just take the whole matrix and multiply everything you see by that power. Yeah. Okay, so yeah, it's as simple as it sounds. And now equally simple. So we extend this to a map of the group ring. So that pi 1 S3 minus k 2. Okay, so what's I guess most people know what's a group ring, but I'll just remind you. So that just means elements in here or well, formal linear combinations of elements in the group. So here G is an element in pi 1 of S3 minus k, and then AG is just an integer. Now what you can do is, well, there's only one thing you can really do, namely you can apply your phi alpha to each G, and then you just sum up again. Why not? And what you get is, well, you get again a matrix with entries in C to the inverse, but you lose invertibility. So you just get some map, you get a map to the n by n matrices with entries in C to the inverse. Okay, so super harmless the construction. Okay, and now what we do is we just take that definition here of an invariant, and we just replace the phi by a phi tensor alpha.
Is there any structure theorem for these group rings?
Say it again?
Is there any structure theorem for these group rings?
Oh,
The group rings of a finite group is.
yeah, but these are more or less a mess. Many of them infinite non-abelian groups. That's not really.
These are finite sums, right? Yeah.
They're finite sums, yeah. So group rings always are finite. So yeah. So yeah. So group ring always means finite linear combinations. Because you need finite linear combinations
Is
to
there any
do.
structure theorem for some?
Yeah, no. Yeah, that's pretty hopeless. Now there are a few things you know, for example, like you know that pi1 is torsion free, and then you know in this setting that these group rings will be domains, meaning they don't have zero divisors. You have a couple of theorems, but in general it's very hard. Okay, and so what we want to do is we basically just take that definition again, and we where we wrote a phi before, I now just write a phi times alpha. Okay, so definition.
Pi cross alpha on the right hand side. Pi cross alpha applied to G.
Yeah, so so that's so the phi tensor alpha is just so it's like sometimes I use a yeah, you do the most naive thing. You just extend them from sometimes it has nothing to do with my particular situation. You just have a representation of a group into SLN something, and then you have the obvious extension from the group ring to now matrices. You can no longer assume that invertible matrices. Okay, so perhaps let k and pi as above. So meaning I just want to continue with my setting here. So we have a not k, we have a representation for pi1. Again, the phi is just given by the abilization, and let me just stress that we have a representation pi1 of S3 minus k to SLNC, and I just write the same horrendous expression, just make it slightly more horrendous by throwing in an alpha. So we okay. So again, I have to pick an I such that phi of xi is non-trivial, and we define. So now tau k alpha. So now put in an alpha to remember it's an invariant which depends on k and my representation. And okay, so now we take okay, so all partial derivatives. Okay, so these are elements in the group ring. I apply phi tensor alpha. Let me just do one minor trick. So, okay, okay. So here we have our matrix with entries in the group ring, and I first throw out the ith row. So, okay, so remove ith row, and then I have a square matrix. And now to each entry is an element in the group ring, and I replace each entry again by an n by n matrix. So what you have here is you start out with so there was well, I used my k too many times. Well, so there was a k minus 1 by k minus 1 matrix with entries in my group ring. Now each entry gets replaced by an n by n matrix with entries in my Laurent polynomials. So now I have an n k minus 1 by n k minus 1 matrix with entries in my Laurent polynomials. So I'm now back to a matrix, square matrix with entries in a commutative ring. So it makes perfect sense to just take the determinant. Okay, so you just take here determinant. And again, we have to compensate by, because we picked some random xi, and I just read it slightly differently. Now what we do is to take phi tensor alpha I, xi minus 1, and determinant. Or another way of saying it is, I mean, if you apply phi tensor alpha to 1, that's just the identity. So just take your xi, apply that that map here and remove and subtract the identity. Okay, so a little bit more messy than before, but not much more messy. And now the obvious question is how about the properties here? How are we doing? So proposition. Well, okay, so one. So tau k alpha is well defined. So meaning as an invariant of the knot k together with representation. Well defined up to, well basically gets same statement as over there, up to multiplication by plus minus t to the k. So here it's, okay, of course I'm not going to do the proof. What is important is that I deal here with special linear representations, meaning the determinant is 1. So if we had here a representation in GLNC, you would get some extra factors. So yesterday we were discussing about various definitions of invariance, and we were saying, well, okay, like the Alexander polynomial has many different definitions, and one way of doing it is, well, you just look at the Alexander module, meaning you go to the intrinsically covering, look at its homology. It's a module over Z3 inverse, and then you can just do your usual algebraic formalism to get some invariant. Now, in principle, you could do something very similar here. So you could you take that data, and then you have what's called a twisted homology. It doesn't really matter what's precise definition, but you can sort of define a twisted version of the Alexander module. Now, since I work here over C to the inverse, it's going to be a module over C to the inverse. And now you can again, modules over C to the inverse are easy because C to the inverse is a PID. So you can just write as a direct sum of cyclic modules, and then you take the product of the corresponding terms, which is the same invariant as what I wrote down here, with one major difference, namely, if you do it homologically, that is only well defined up to multiplication by a unit in the C to the inverse. So, and here I have a small indeterminacy. So if you do the homological definition, it's only well defined up to, well, power of t and multiplication by a non-zero complex number. And so with this setup here gives me a smaller indeterminacy. Okay, let's see. 2. Okay, how about symmetry? So now I have to write here my representation. So here I have my representation alpha. And so if you want to do symmetry, it's a technical, which we will not talk much about them, but it's subtle. So if you want to do symmetry, like I was saying, like for the Alexander polynomial, it's a consequence of Poincare duality. So symmetry of the Alexander polynomial, like whichever way you define it, at the end of the day, it's some consequence of Poincare duality, more or less in disguise. Depending on how what's your favorite definition, what's your favorite proof, it's that Poincare duality is more or less well disguised. But at the end of the day, it's Poincare duality. And now here, if again you can cleverly use some Poincare duality, but then if you work with the twisted coefficients, you have to be a little bit careful because the representations will might change. And so here, let me just, it's really not an important point, but just to show it, one has to be a little bit careful with these things. So here alpha star is the representation which is given by alpha G inverse complex conjugation transpose. So it's a little bit delicate. Okay, but let's not get hung up on that issue. And the remaining statements here basically generalize in the most obvious way. So 3, the degree of these twisted invariants. So perhaps I should just call it twisted Reidemeister torsion, or sometimes also called a twisted Alexander polynomial. So there's a lot of literature on twisted invariants, twisted Reidemeister torsion, twisted Alexander polynomials. The invariants always differ slightly, but let's not worry about it. Okay, so now what you want to say is, again, you want to relate the degree to the genus. And like yesterday was sort of outlining the proof. You just take pi 1 of not complement, have a Seifert surface, cut along it, and then you get some H and N extension of your pi 1, and then you apply the algorithm with the representation, with the presentation which comes from the H and N extension. You just stare at it for 5 minutes, and at the end you see the formula here. And you do exactly the same proof. Nothing changes, except that you pick up a factor of n. So you get here less or equal than n. Oops, sorry. So yeah, that's correct. So you have your n-dimensional representation somehow. If you go through your proof, you somehow see everything gets larger by a factor of n. So you get here an extra n. And 4, I will not even write it down. You just get it as the obvious analog of 4. If it's 5, but you have equality and things are monic. Okay. So that's not so bad. Okay, so the question is, what does it do for you? Now, okay, there are two different types of questions. One is you have 2 different knots and you want to distinguish them. And then another question is you have a knot and you would like to know some properties, like you would like to know, is it a fibered, what's a genus, and God knows what. So let's first start out with a question like, we have a given knot K, and we just want to know what's happening with that knot here. So then you can just try to find the representations alpha. And how do you do that? There's a clever way which we'll talk about in 5 minutes. There's also simple-minded way which works surprisingly well. Namely, let me just give you an example. E.g. So it's one of these stupid tricks which sometimes are surprisingly useful. Namely, let's say you have an epimorphism or homomorphism to a finite group. Okay, and that's actually easy to find. Like if you have a presentation, take your favorite finite group, like symmetric group on S5 or whatever, and then you can fairly easily check whether you find an epimorphism. You just have your presentation here, send it to generators to S5, and with a little bit of luck, you find such a homomorphism. Okay, like I wrote a computer program at some point to implement some of these algorithms, and you don't want to do it by hand, but the computer can easily find non-trivial epimorphisms onto finite groups. And now you have the most stupid trick, which works really well, namely any finite group comes with its preferred representation, namely you just operate on the group ring. So you just go here to automorphisms of the group ring. So here's a group ring here. It's it's a G is a finite group. So the group ring is just a finite dimensional vector space, and then then G acts on here just by a left multiplication. So you immediately found representation. So and then here that's it goes into it depends what you mean by order at that point. So you just go here to SL order of G C. Okay, it's one of the tricks which are really useful in mathematics. If you have a finite group comes with a super nice unitary representation. It's a trick to remember. It's really useful.
But why should it be in SL? It can have determinant -1 also. That automorphism.
Okay, you're annoying.
Ignore the questions.
So is there a good notation for representations which have determinant ±1? So yeah, I mean, fair enough. Yeah. So to get my indeterminacy here, it's actually enough to go into say a representation which have a determinant ±1, and I guess there's no good notation. Otherwise, what you can also do is if you have a representation which has a determinant ±1, then you can just add one extra dimension and compensate them. But you're right, so it's yeah, okay. Yeah, okay. Fair enough. Okay, so that's something you can do, and back in the day when I was a postdoc and still had time, so I wrote a computer program which take a node and plug it into the computer program. The computer program tries to find such representations. It computes these twisted invariants. And like in all cases which I tried, you give any node, you would always find a representation which such that, for example, like here you get equality. So that's like something which I did like 15 years ago. That given like wrote a computer program, took all nodes up to like 12 crossings, and it would always find a representation of that type here, such that you get equality. Now the question is, can you always do it? Like given any node, will there always be a representation such that you get, say, equality at that stage? It turns out that's actually true. So that is, I guess we no longer need the definition. So let me just mention. So there's a theorem by myself and Stefan and Vidusi. So given any k, there exists a representation alpha such that here you have equality. So degree of tau k alpha t equals so n is my representation of my dimension of the representation 2gk minus 1. Evidently, I will not go into the proof, but let me just say one key word. Like if you look at the history of three-manifold topology, there are a couple of like major steps. There's like late 50s, something called the loop theorem, Dean's lemma, sphere theorem. Then the next key step perhaps is Thurston generalization, which was proved by Perelman. And then there's like the third key step in three-manifold topology is proof of virtual fibering theorem by Agel and Weiss, and that goes into that proof here. So uses a virtual fibering theorem of Agel and Weiss. Okay, so I don't want to go into that, but so it uses some heavy machinery, which was proved like 8 years ago, so by Ian Agel and Danny Weiss. And once you have that, okay, you need to know what you need to do, but like afterwards you need to be competent to prove the theorem, but would never have been possible to prove that theorem without Agel Weiss proving virtual fibering for three-manifold sum. Yeah.
Do you have any bounds on n?
Okay, it's a perfect question to move on to the next topic. Okay, so Albert immediately found the flaw in the theorem. Uh, so the flaw in that the theorem is okay. I give you an odd k, and I tell you figure out what's the genus, well, okay. So now you know there exists a representation which will detect the genus. The only catch is we have no idea what representation to take. Okay, so like we have no bounds on the dimension. Like we have no bounds on n, because basically, so the n. So basically, let's just say 1 second. So you have your knot k, and then you need so angle-wise give you some finite covering, which is going to be fibered, and our n is at least the degree of that, was actually precisely the degree of that covering. But the angle-wise is totally God knows how big it is. So yeah, so could well be. So in practice, it seems to work even for small values, but the theoretical upper bounds are at best horrendous. Okay. So it works well in practice. Like if you have a knot k, what you can do is you can basically do two things. You can take a computer program which spits out Seifert surfaces, which people like I guess Nathan Dumfield perhaps has written a computer program. So then it gives you lower bounds on the upper bounds, lower bounds, upper bounds. Anyway, it gives you bounds on the genus, and from us you get the opposite bounds, and then with a little bit of luck you meet, and then you get the genus. So in practice works well, but in theory it's awful because you have absolutely no idea how big is the representation. No. So that works for actually that works. So perhaps I should here also mention one more name, namely Szytycki Weiss. So we need so there's virtual fibering theorem for hyperbolic manifolds due to Agile Weiss, but there's also virtual fibering for 3 manifolds which have a boundary. And that's due to Szytycki Weiss, and since it's a knot theory conference, one has to be careful when you say Szytycki, because there are three, at least at the latest count, at least 3 Szytyckis, and so that is Piotr. So Piotr is a nephew of Joseph, as far as I know.
Can you give some intuition why the degree of the cover is giving you the dimension of the representation?
Well, okay, so you have an odd k, and if it's fibered, it's easy to determine the genus, because then you already have actually even have equality here. So if it's a fibered knot, everything's easy. So and now, so what's the idea? So you have a non-fibered knot, and now what Agile, Weiss, and so on tell you is it exists a finite covering. And now, I guess you know about the Thurston norm, sort of. Anyway, so you just look at them. You have your class in H lower 2, which comes to your Seifert surface, and so general statement of virtual fibering theorem is you have a reasonable manifold, 3-manifold. Forget about knot complements. You have a class phi in H lower 2, and what Agile and so on tell you is there exists a finite covering such that the pullback of that class, which is again a class in H2, can be approximated by fiber classes. Like an element in H2 is a fiber called fibered if it comes from a vibration. And what Agile Weiss tell you is given any reasonable 3-manifold, given any class phi, there exists a finite covering which is fibered, but not just in some random way, which has nothing to do with the phi, which would be useless. But you can actually you can approximate your phi by fiber classes. And then for fiber classes, you know, we can easily determine them first norm genus using Alexander polynomials, and then now you have to do a little bit of limiting argument. You have to do a couple of tricks, algebraic tricks, which makes our paper into a paper and not just a corollary. But that's sort of the main idea. But so that's perhaps something which is, gets overlooked. So virtual fibering says not only there exists a finite covering which is randomly fibered, but actually given any class, any surface downstairs, there exists a finite covering such that you can approximate it in a reasonable sense by fibered classes.
Where do you get the dimension of the representation?
So basically, it's you go to your finite covering, which is fibered, and up there, so you just look at Alexander polynomials of your finite covering. Now you have to look at multivariable or whatever. Then actually up there, with a couple of cheap algebraic tricks, you see you only need a one-dimensional representation to do to detect genus. And now what you do is your representation is just an induced representation, like it's just the old. Okay, another great trick in representation theory. I only know two tricks when it comes to representations. One, a finite group gives you a representation, and the second trick, which everybody should know, is if you have a group G, you have a finite index subgroup H, and if H comes with a k-dimensional representation, then you get an induced representation for your bigger group, and the dimension multiplies them. Best trick ever. And that's basically what's happening. It's basically a one-dimensional representation of some finite index subgroup extended, induced over the whole group. So I mean, you have to do a couple of things, but at the end of the day, if you know what you're doing, it's a couple of standard good tricks. Okay. Now, okay. So what about Abhijit's question? So what you really would like to say is you would like to know which representation to take. And now if we have a say a hyperbolic knot K, then of course we have we already saw in Abhijit's talk that if you have a hyperbolic manifold, for example like a hyperbolic knot, then it comes automatically with a representation. So let me just perhaps quickly remind you. So recall. So let n be an orient. Let me write oriented hyperbolic three-unifold. Okay, so then we get a representation alpha from pi 1n to the orientation preserving isometries of H3. And what matters for our story is that that is for mysterious reasons the same as PSL2C. And what's PSL2C? So that is just SL2C modulo plus minus identity. And as Abhijit mentioned, there's so if a knot is hyperbolic, it actually has a unique hyperbolic structure. So there was a Mostov rigidity. So that representation here is actually up to conjugation canonical. So you have here you have a unique, faithful, and a discrete representation. So here injective and discrete. So you really can talk about the discrete and faithful representation. Okay, so that's promising. Now, okay, so what I want as input is I want a representation into SL and C, and now here we're right now at the PSL2C, and as Abhijit already mentioned, you can actually lift the representation. So meaning, so there exists, perhaps let me just do dotted one. So it turns out you can, so here you have a representation into a PSL2C, and then it actually turns out, we're a bit lucky, you can actually lift the representation to a representation into a SL2C. And as Abhijit was saying, the lift is no longer canonical. In fact, it's fairly easy to see. It's number of possibilities. It's 2 to be one of your manifold. Oh, that's true. So if you have a knot, you have a unique such representation to PSL2C. You have 2 lifts to SL2C. Okay, now you could say, okay, we'll work with both, and but now it actually turns out we're a little bit lucky. We can still specify one of them, namely if we look at a knot complement, there exists a unique lift such that, so let's call it also alpha, such that the trace of alpha of the meridian equals 2. Okay, perhaps not all that important right now, but actually you can specify, you can really specify a canonical lift. Okay, a little subtlety, but okay, so that means that you can actually define an invariant of hyperbolic knots. So perhaps define. Okay, so that's now curly T of K. So here's a hyperbolic of T. So it is just tau K. So let me write here like alpha hyperbolic, just to remind you of what's happening. So that's supposed to be this one here. It's so mu is meridian, and you just the meridian is going to be parabolic, and then it's either plus or minus 2, and you pick the one with the 2, and it turns out there's precisely one with the 2. Okay, so you actually need a situation that for hyperbolic knots, you actually have a well-defined such polynomial. Like you no longer have to worry about what representation to take. There's some sort of a God-given one which is staring at you, and you just grab it. Okay, and what can we say? Well, so you basically have the obvious, well, basically that preposition here just gives you immediately statements for that polynomial for hyperbolic knots. And let me perhaps just add 5. 4 was about a fiber, which is a little bit subtle. Namely, let me just mention it. So, slight subtlety. Okay, so Km was just a mirror image. And the subtlety is, okay, like if you take a knot K, you take its mirror image. Well, okay, there are complements, homeomorphic, but if you go through your this construction here, what you see is that your representation changes from alpha to alpha complex conjugate. So that is here. So if you go from a knot K to mirror image, the representation, the unique canonical representation here, alpha, changes to its complex conjugate. And then the complex conjugation just travels through your whole definition. And then you see that statement here. Okay, perhaps not so exciting. But what it does say is if a knot is amphichiral, so if it's equivalent to its mirror image, this polynomial has to be the same as its complex conjugate. So then a polynomial has to have a real coefficient. Okay, and now it turns out that this polynomial here, in some sense, it is easily computable, because as Abichi was saying, here's this program called Snappy, which does the following. So if you have a manifold, or for example like a knot, then it can determine whether the complement is hyperbolic, and it will spit out the representation alpha. Now, to be super strict, it's well, it's not 100% rigorous. Like, it gives you the representation up to you know, God knows many 500 digits. I have no idea, something outrageous. And in principle, I guess it could be wrong. In principle, it could decide that something is hyperbolic, but it isn't. But in practice, I guess it's never known to fail. So in practice, it works. So in practice, if you have a hyperbolic knot k, Snappy will give you the representation, and then you can easily compute the invariant, but there was nothing going on, as we saw. And then the question is, how good is that invariant for hyperbolic knots? And so let me perhaps just mention. So, calculation. So that appears in a paper of mine with Nathan Dunfield and Nick Jackson from Warwick. So what we did is we calculated that invariant, and if you know the three co-authors, you know it's certainly not I who did the calculation. So it was my idea to do the calculation, and then basically talk to Jackson and Nathan, why don't you do the calculation? And then of course they did it. And what we saw is, for all knots with less or equal than 15 crossings, so you get that the degree of that polynomial here will always correspond to the genus. So you always get degree of curly t, I said, kt equals, now here my representation is two-dimensional, so here factor 2. So for example, like that was sort of the first test case. You look at Conway knot and Kishida-Terasaka knot. So mutants, Alexander polynomial 1, hard to distinguish in general. But actually, one has a genus 2, the other one has genus 3. And okay, we did the calculation. And then actually, you have these two hard to distinguish knots. You plug in the machine, you throw in the machine, and you nicely see that you have a large polynomials with the corresponding degrees. So and there was initial calculations I did with Nick, and once we saw that Kinoshita-Terasaka Conway knot works, we knew we were in good shape. Okay, so secondly, it always detects a fiberedness, so it's like the polynomial is monic if and only if it's fibered for all knots up to 15 crossings, and also for knots up to 15 crossings, this invariant is a real polynomial if and only if it's amphichiral. And the obvious question, of course, is okay, does it work for every hyperbolic knot? And I have no idea. So if anybody has great ideas, talk to me. Okay, thank you.
I mean, that representation lifts from PSL2C to SL2C?
Yeah.
It always does?
I think it always does for orientable free manifolds. I'll try to prove at some point, yes. Don't ask me right now how it works. So I think you have the representation to PSL2C. If I remember it correctly, it always lifts if you have an orientable hyperbolic manifold.
Representation sufficiently close to the canonical or discrete faithful representation.
They all lift.
Just by a result of color.
But you need orientable manifold?
Well, I would put that adjective in, but I don't know.
Uh-huh.
It's well, probably you do, because otherwise you're going to have a two-torsion problem, no?
The lifting of representations is parameterized by the H2 of the manifold in C2 class.
No, but that's that's how you count the number of liftings. Like if you have one lifting, all other ones differ by that set. But
But if you have two torsion, if you have sufficiently or if you have if your orientation reversing and you have a sufficiently faithful representation, then I think you're going to have an obstruction, because you'll probably have a non-central element of order 2 in PSL2C, and then that representation won't work. So I imagine that generically you need it to be oriented.
For orientation, for three manifolds, lifts a result of marked color shows that they always lift. The discrete faithful representation. For knots, it's really easy to show explicitly that it lifts. You're lifting every vertical generator, the meridian, and as you go along the knot, you can just choose the sign, making sure that and as you come back, you can see that the sign is determined.
Oh.
For the for knots, you can explicitly see the lift.
Oh, I did. Okay.
Walking around the knot and lifting the generator.
Or if you like the algebra, the knot group decomposes into two cosets pulled back from the surjection to Z mod 2Z. And the even coset always lifts, there's a unique way to lift it, and then the odd coset, you get two lifts, one for each side.
Okay. Okay.
Right.
Any other questions? Sir, in your theorem with Lucy, the representation you get is this one, right? Only just from each other one? If it's a hyperbolic knot?
Oh no. So now we have some. So basically, two sources of representations which I know. One is some discrete faithful, and the other one is a trick of go to some finite covering, perhaps take an abelian representation there, and then induce it to downstairs. That's the two representations which I understand them. And the one with the Vidusi is finite covering abelian representation induce them.
Okay, this line is taken.
Yeah.